So what we'll be looking at is the idea of solubility, and then measuring a particular numerical value that can represent the different solubilities of ionic compounds. So we're specifically looking at solubility of salts or solubility of ionic compounds. Now, be it an ionic compound or covalent, when you dissolve a solute in water, you got a solute in water, it dissolves to give you a solution. That's what we know how to make solutions. You have a solute, which is what dissolves in the solvent. The solvent is always a liquid. Many times it's mostly water. At times it could be oil or alcohols, depending on do you want a polar or non-polar solvent. Water and alcohol are polar solvents, while oils and fats are non-polar solvents. Even alkanes are non-polar solvents. And solutes dissolve in solvents to make a solution. And in most cases, in this particular chapter, we'll be looking at ionic compounds dissolving in water to become a solution. Yeah? Now, this stuff everybody knows. What I want to talk about is what's happening at the particle level. So here what you have is a solute. Here is a solvent. These are, for example, this is an ionic compound. So let's call this solute an ionic compound. And right on top is your solvent. Now the solvent is, in this case, let's take it to be water. So each of these blue balls is water molecules, and each of these orange balls is either a positive or a negative ion. And when you take these guys, you mix them in water, the ions separate, and you'll find these orange particles are surrounded mainly by blue molecules. So this is what a solution at the atomic or ionic level looks like, at the kinetic level. So that individual ions of the ionic solute are mixing around, and most of they're surrounded by many of these blue molecules, which are water. And this is your solution. So at the kinetic level, at the atomic and ionic level, this is what the solution looks like. The solute obviously is always fewer in particles in the solvent, because solvent tends to be larger. Not always, but it always generally tends to be larger in amounts. So this is what you have: solid mix in with solvent to give you a solution. Now, how this comes about, we've discussed some of it in energy and hydration and solution, the enthalpy changes involved in such a reaction. And now we're going to be talking about this particular change in more detail numerically. So a little more detail regarding this. So now, if you remember, when we decided to do solution and hydration, one basic example was that sodium chloride can dissolve in water to form aqueous ions. Now, very soon this reversible sign will be obvious to you, but you can ignore that for now. When that happens, what's happening is, when sodium chloride ionic compound dissolves in water, each individual sodium and chloride ion is going to make bonds with water. And it's this bond formation that actually results in hydration, energy being exothermic. That's what gives the energy to break these bonds. So in most cases, if you remember, there was bond energy required to break the bond, that was lattice energy, and new bonds are formed through hydration, and the overall reaction was called delta-H solution. And some reactions had very endothermic delta-H solutions, and some reactions had low endothermic or exothermic. And we had said that those that had low exothermic or low endothermic, those compounds were highly soluble. They would tend to dissolve. Now, this chapter that we're dealing with is really about partially soluble salts or sparingly soluble salts. And just to explain that, I want you to remember this, that what was happening at the ionic level is that the ions separate and they make bonds with water. Now, NaCl is completely soluble, but that's not the case with many other ionic compounds. What I mean to say is that, yes, so far we've seen this. We've seen this basic idea. You take a solute, any piece of solid, mix it in this water, and it becomes a solution. I think these are swapped. Sorry. So you got, this is a solvent and a solute, they become a solution. The other part is easy. But what happens is, depending on how much solute you want to dissolve, you can keep on dissolving the solute to make a more and more concentrated solution. And you have what we call two types of solutions. Either you can have an unsaturated solution, which means that you can dissolve more solid, but if you keep on dissolving more and more solute, there will be a point that no more solute dissolves. So you add the next lump of the solid and it will not dissolve, which tells me that the solution that's remaining, you see this darker pink is darker because more has dissolved here than here on the left hand side. And this darker pink solution is now what we call a saturated solution. And this chapter will be dealing with such solutions, saturated solutions. And what are saturated solutions? These are solutions in which no more solute can dissolve. You've tried adding more and more and more solid. Eventually, it will remain undissolved at this moment. You can get a solution only by removing the solid using filtration. Simple filtration will remove this solid. And the remainder solution is your saturated solution. So that solution inside is a saturated solution. And we're going to be talking about such saturated solutions between different, you could say, partially soluble solutions or sparingly soluble solutions. So let's talk about an insoluble salt, a salt that we would consider insoluble. That salt, one example is, we've seen that in group 17 in the AS level, is silver chloride. Now silver chloride can be made by precipitating silver ions and chloride ions together, or you mix a solution with silver ions with the solution that has chloride ions, and they will combine to form a precipitate called silver chloride. We had seen this with silver nitrate and sodium chloride, maybe forms a white precipitate of silver chloride. That stuff we know, right? What I do want to talk about is that what we also now know is that silver chloride, if you take solid silver chloride, and for example, you take, I'll take solid silver chloride and I add it to water. A very, very, very small amount dissolves. In fact, a very, very small amount dissolves to form aqueous ions. And we can prove that by passing current through this. So the thing that we thought was insoluble, silver chloride, is in fact very minutely soluble. So you take silver chloride solid and add it to water and mix it. To the naked eye, it might not look like it's mixing. But what happens is a very small amount of it dissolves. So you can say a very small amount of silver chloride does dissolve. And it's proven by the fact that if you were to pass current through that solution, you could. Which tells me that the solution would have ions, and the ions could only have been silver and chloride ions. And what we now know is, in fact, that solution in which you take a solid, so for example, you take a beaker of water and you add silver ions. So let's say I take a beaker of water and I want to add, in this particular case, I will add white silver chloride. So if I add white silver chloride, and it will make a lump at the bottom, and a very small amount of this white will dissolve in the solution, and that solution will now be able to conduct current. What we have just made, by the way, is something called a saturated solution of silver chloride, because it took only a small amount of silver chloride to dissolve in this. So the solution was a saturated solution of silver chloride, and most of the silver chloride remained undissolved. So when I take an insoluble salt, it really is very, very slowly soluble. You add it to water, a very small amount of the solids ionizes and dissolves in water. So the water has a very low amounts of the ions. So you might get a very, very, very small amount of some silver ions and some chloride ions. You would have that in this region. Now, it's not enough for you to really see, because most of the salt remains undissolved, but because no more dissolves, because it has reached saturation. So the idea is that the reason why we call silver chloride an insoluble salt is because a very small amount of silver chloride is required for saturation, and the remainder amount stays undissolved. So to the naked eye, it looks like insoluble salt. But every insoluble salt is somewhat sparingly soluble. It dissolves a very, very small amount, and in the solution you're going to find those ions. But the beauty is, this solution is what I'm concerned with, this saturated solution of a, let's say, silver chloride, because there's some beautiful magic happening there.
Quick pause. If you're finding value in this explanation, there's so much more to discover at Alt Academy, where we break down every A-level concept with the same clarity. Now back to the video lesson.
So let me show you. Now, for example, what we found was that saturated solution of silver chloride is in fact silver chloride solid in equilibrium with a saturated solution of silver chloride. Now what's happening at the ion level is this. It's a nice little diagram. Tells you what's happening. So this is a cross section of the surface between the solid silver chloride and the saturated aqueous silver chloride. What happens, and what we now know for to be true, is that when we say we've made a saturated solution of silver chloride, and that as much of silver chloride that had to dissolved, and the remainder remained solid in that beaker, there in fact is literally an equilibrium between silver chloride ions and silver chloride solid, aqueous ions and solid. So there's a rate at which these silver chloride starts to dissolve in water. So you'll notice silver chloride, silver ions are going into the aqueous form, and there's a rate in which the aqueous ions are becoming a precipitate. And the idea is that in every saturated solution, that's what happens. That there is an equilibrium between the solid and the aqueous ions in a saturated solution. And that is what the crux of this whole chapter is that to talk about this equilibrium that exists between the undissolved solid and the aqueous ions. And we know it's an equilibrium because even though the amounts don't change after the equilibrium, it's a dynamic equilibrium because the rate in which the silver chloride is dissolving into aqueous form is equal to the rate in which the silver and chloride aqueous ions are reprecipitating back into silver chloride, because we know silver and chloride ions do precipitate to make silver chloride. So really what we're saying is that in this equilibrium, the rate at which silver chloride is dissolving is equal to the rate in which silver chloride is precipitating, which is why the amounts don't change and they become constant. And that happens only and only at saturation. So this is the idea of what we call solubility product, the idea of the equilibrium between an ionic solid and its aqueous ions in water, given the solution is saturated. This will not happen if the solution is not saturated. And this equilibrium is not just for silver chloride. It could be for any saturated solution of a sparingly soluble salt. So if you can think of this as a generic medium. So here I have a beaker on the left hand side. Now this beaker represents the saturated solution where the remainder undissolved solid sits right here. So this undissolved solid of any solute in a saturated solution will sit like this because no more of it will seem to have dissolved. And imagine this to be a compound called XY. So this is compound XY solid. This fellow right here in the red. And the X has a charge and the Y has a charge. Let's say the charges are equal. It doesn't matter what the charge is. But what's happening is the rate in which X and Y are going into solution at this surface is equal to the rate at which the ions are reprecipitating back into this lump of solid. This would happen with silver chloride. This would happen with silver bromide. Take all your insoluble salts. Calcium hydroxide, the white PPT. Barium sulfate. Iron 2 hydroxide. Iron 3 hydroxide. All those guys that we consider to be insoluble that we have seen in salt analysis theory also, where they precipitate, different color precipitates. All those precipitates are actually solids in equilibrium with their saturated solution. And at the surface of that, there's a constant equilibrium where there's a rate in which the solid is becoming aqueous is equal to the rate at which the aqueous is becoming solid again. And this is true for all ionic solids. Now, how do we know this to be true? Well, you can imagine an experiment like this, where, for example, I'm talking about lead chloride solid. Now, lead chloride solid dissolves to form lead and chloride ions. Now, it's a sparingly soluble salt only. It doesn't dissolve too well. But here I have two set of beakers. This is the before setup and this is the after setup. So to prove that there is a dynamic equilibrium taking place, if you take solid lead chloride with non-radioactive lead chloride, mix that with a radioactive isotope of lead chloride solution. After some time, what happens is that some of the radioactive lead chloride is now going to be found in the solid, and some of the non-radioactive lead is going to be found in the solution, which is proof that there is some dissolving and some precipitating taking place, even though we started off with the saturated solution of lead chloride. So the saturation didn't change. What changed was the actual particular ions that are in solution. In the left hand case, you had only the radioactive ions in solution and the non-radioactive not. But over time, if you leave this to be, then the ions swap because it's a dynamic equilibrium. So you can take this as proof that this was really happening. Our concern is really very, very small in this chapter. We have to find the mathematical value for the equilibrium constant for such equilibriums. Now, equilibrium constants you've done in AS level. Those are called KCs. And we are going to be now specifically talking about the KCs, in this case, for such equilibriums. The equilibrium between an ionic solid and its aqueous ions. And that's what we're going to talk about next. Yeah. So let me show you some more equilibriums of saturated salts. Now, for example, you just saw silver chloride, and lead chloride. You could take any ionic solid and you mix it in water, the one that are sparingly soluble. You mix enough of it, there will be a point where no more will dissolve and you have made a saturated solution. And at that point of saturation, you're going to have the solid in equilibrium with the aqueous ions. So for example, if you made a saturated solution of silver bromide, you're going to have silver bromide solid in equilibrium with silver and bromide ions. That's an equilibrium. And the idea is that every saturated solution will be that, an equilibrium between the ionic solid and aqueous ions. Things like barium sulfate. Barium sulfate is also insoluble. You see, it doesn't dissolve. It's a white PPT we heard, right? It's sparingly soluble. So if I have a saturated solution of barium sulfate, then at that moment of saturation or the point of saturation, the solid barium sulfate will be in equilibrium with aqueous barium and sulfate ions. And that equilibrium will exist. Must be that very, very, very small amount dissolves, but it still dissolves and there is an equilibrium. And we will use this to our advantage later on in the real world. It's a very important equilibrium, but it exists. It doesn't have to be in 1:1 ratios. You could have, let's say, a saturated solution of aluminum carbonate, of, let's say, Al2CO3 thrice. This guy is insoluble in water. And so, let's say, it's when you have a saturated solution of this fellow, when a very small amount dissolves in water still, because even if we call it insoluble, it's very, very, very sparingly soluble, technically speaking. And so what happens is a very small amount of it will dissolve in aqueous form to form such ions. 3 carbonate ions, 2 aluminum ions for every mole of Al2CO3 thrice, because Al is 3 plus, CO3 is 2 minus. Now this equilibrium can also exist for a saturated solution of Al2CO3 thrice. Again, and we'll be studying this equilibrium position really. We'll be studying the Kc values of such equilibrium positions. All right? And that's the first idea here, is that every sparingly soluble salt dissolves in water, forms an equilibrium during saturation. At the point of maximum dissolving, at the point of saturation, no more solid will dissolve, and there will be a rate equivalence, or the rate at which the solid dissolves is equal to the rate at which the ions precipitate. And that equilibrium is what we are really interested in, really. All right?
Hey there. If you found this A-level chemistry lesson helpful, why don't you head over to our website, altacademy.org, where you can sign up for the full A-level chemistry course. In addition to chemistry, you can sign up for physics, biology, math, or 4 other A-level subjects. Thousands of students have already taken the leap. What are you waiting for?